Okay, can you see the slide?
Boleh, Prof.
Okay, so this is another classifier. So the secret behind this instant-based classifier is they measure the similarities between the new unseen data with the sample data that they have in the database. Okay, so they require this K because the K refer to number of nearest neighbor that you want to compare with the new unseen data set. Okay, so this is also called lazy learner because we do not do any modeling, but instead we measure the similarity of two examples using equivalent distance or the cosine distance. Okay, so they call it K and N because the K is the a variable that hold the number of nearest number that you want to use compare. Okay. So nearest neighbor classifier are defined by the characteristic of classifying unlabeled example by assigning the class of similar label example. So it depends on, okay, if we have new instant here, then we want to check, let's suppose our K is 3. So the nearest neighbor is this and this and this. So we look at the label here. If the label is A and B, so the majority is A. So we use and we say the new label for this new unseen data is A. Okay. So k-nearest neighbor is very powerful, but they require a lot of computation for the distance that we need to compute. Okay, so they can use for optical character recognition, facial recognition. This is for music or movie recommendation. We look at the pattern in genetics. So a very powerful one can be used in any of the method that we have in any of the tasks that require classification. Okay, so if a concept is difficult to define, but you know it when you see it, then nearest neighbor might be appropriate. Okay, so the instant based learning is looking at this one. They look at for all the data that you have, they have the class label. Okay, so if you have a new query or new sample here, so the first thing that they need to do is to locate the nearest training example, and we assign the label to the new unseen data here depending on the majority of label that we have. Okay, so if we say k equal to certain value, so we will take the vote among the k nearest neighbor, and then we will assign the label that have the majority number that having that label, and we will assign them to the new instant here. Okay, so basically we just counting lah. Okay, so this is the number of k, number of neighbor that we have. So if 2 out of 3, so majority, so we will assign this label to the new instant here. Okay, so what happened in KNN algorithm? We basically compute the distance between the unseen data with your data that you store in your database. Okay, but first we need to define what is K. So up to you lah. So the unlabeled test instance is assigned the class of the majority of the k nearest neighbor. So if k is 3, we need to find the label for each of the nearest neighbor, and we assign the label which has the majority label. Okay. So for example, like this, if we plot the ingredient and based on sweetness and crunchiness, and this is the class label that they have. So um, so this one we illustrate them in 2D. This is will tell them what class they have. So if we have a new one here, so we will decide the label for this depending on the distance to the nearest neighbor that we have. Okay. So the advantage of KNN is that the training is very fast because they just use distance. Basically, they measure the distance between the unseen data to the data that you have in your storage. And learning complex target function, they can learn complex target function easily because they are only they are only using the distance method. Don't lose any information. This is slow because you need to compute the distance from one new data to the rest of the data that we have. So if you have 1 million row in your data set, so you need to compute the one, um, 1 million times. A lot of storage because you need to store all of them easily full by irrelevant attribute because they are using distance. They are using the similarity here. So if you have attribute that has outlier or different value, it will affect your classification. Okay. So for the distance that we can use Euclidean distance or the symbolic one. For the numerical one, we can use the square root of the difference between the um, value belong to different vector here, and then we take the square here. We over here we say n equal to 2. Okay, so basically we are summing up the square value of differences between two instances, and then after that we take the square root here. This is for numerical features. Okay, but for the symbolic one, we just use 1 or 0. Okay, so if they are 1, no, this is different. This is value difference measure. So this is basically looking at given the value I here, what is the probability of having that uh, class that we have. Okay? And then we minus the given the minus the probability given that we have that value j. What is the probability of having uh, the class h here? And then we take the um, this is the number of it could be 1 or 2 and so on. Okay, so to normalize the minus value, the best one is 2. Okay, so these are the distance measures. For example, we go back to the example just now. So these are the new instance that we have the tomato. Okay, so the tomato one we have sweetness 6 and crunchiness 4, and then now we want to measure the distance between the tomato and the what the green bean. Yeah. Okay. So we take the value is 4.2. Okay. So but we need to compute for the rest of them. So this is the distance that we have. Okay. So if k equal to 1, that means this label is assigned to tomato. If the k is 3, that means we take the top 3. So we have 1 fruits, protein, and fruits. So majority label is fruits, so we assign tomato as fruits. Okay. So it all depends on k, number of instant that you want to associate them with the new instant that we have. So we just use equivalent distance to measure. Okay. And they say defining k is another issue. They say that if your k is this is what we call underfitting. Underfitting means you have low and low. During training, you have low accuracy, and also testing also you have low accuracy because you are not fitting the sample data here. So this is balance. This is overfitting because during the training is low, no, high. Okay, training is high, but during the testing you have low because you are too strict. So this is what we call overfitting. Okay, so to avoid underfitting and overfitting, we want to have a balanced one. So what we want to do is we want to have the best value for k. Okay, so if your k is more, so that means you will have underfitting. If your k is smaller, then you will get overfitting. Okay, so what you want to know is you want to know what is the best k. So not too small, not too big. So here is another example here. So larger k, which means that you have more to cover. So that means you measuring this and this and that. Okay, for that reason you have low accuracy under fitting. Okay, but for this one it's overfitting because you have a smaller k here. So you are too strict, and for that reason, your training sample would be training result would be low. Okay, so smaller value of k allow more complex decision, which is this. That will cause you overfitting. Okay, so the problem is that we do not know whether the straight boundary or the curve boundary better represent the true underlying concept to be learned. So what we can do is we can look at the let me fast forward. They don't have it here. Yeah, it's okay. Okay, so and again, when we measure the distance, basically they depends on the value of individual column, right? So if you have salary and age, salary will have bigger impact compared to age because the differences between two samples for salary would be too big compared to age. So for that reason, we need to normalize your dataset. So we can normalize using the min max ataupun the z-score. So the aim of this is to standardize the range of value that we have. So for all the column that we have, we will have value between 0 and 1 only. Okay, so this is we take the mean of the column and also the maximum of the column. Okay, so for each of the value that we have in that particular column, we perform the normalization, we get the new data here. Okay, so this is using the standard deviation and mean. Okay, so if we have symbol, so if they are male means 1. If they're female means 0. So not the same. If they're the same, you put 1. If not the same, 0. Okay, okay, so why can any is called lazy? Because there is no modeling. Basically, you are using the distance method in order to measure the distance and determine the label of your new instance. They say that the more column you have, the more feature you have, it will affect the calculation, right? Because you need to compute for every column that you have in your dataset, you need to compute the differences. Okay, so imagine instance could be described by 20 attributes or 20 features, but dua saja yang relevant. So how do you solve the problem? Okay, so we do not want to include all the features that we have. So one of the way for us to look at how do we solve this one is we look at the normal distribution, uniform distribution, point hypergrid, approximation of sphere by cube. Okay? But all of these things we can shortcut, and we look at the entropy. We have shown the how to compute the entropy. So for each column that we have, we can use the value of individual column to determine the entropy. So the entropy or the features that provide you the highest IG, meaning that they are more important compared to the other features that we have. So meaning that if you have 10 features, you will compute the entropy for each of the features, and then you can have a threshold saying that all the features having IG more than 0.5 will be remain for the modeling. So that's how we form feature selection to reduce the number of features in your data. Okay, so for the feature selection, we have two approach. The first one is called filtering approach. So the one that I described to you is called filtering because we look at the info gain and then we set all the features having info gain more than 0.5 will be included in the modeling. So this is filtering. Okay. The wrapper approach is similar to the filter, but except that we are using different algorithm. Let me show you here. So this is filtering. So what happened when we look at the result that we have? This is your space of features subset. Okay, you want to do the selection of the features. So you will select the feature and try to do the training and testing here. And then at the same time, once you get the best feature subset here, you will use the same algorithm that we have here to learn the model based on the test data set. Okay, so di sini we are looking at this is different. Okay, different function. This is different function. So meaning that we have algorithm A, algorithm A1 and A2. So this way we can use the entropy. And this one, depending on the machine learning that we have, the classifier. So this way you just do the filtering based on the IG. We also have the wrapper. The wrapper here is basically we we test the combination of the feature here, and then we do the modeling and testing. Then we look at which combination of feature that can increase the accuracy here. So we are in a circle here. So once we get the best set, basically we are using the same algorithm here. Okay, so they call it wrapper because you do the feature selection using the same um, machine learning algorithm that you use to perform the testing. Okay, so this one is during my study, I look at how this filtering and wrapper approach are different and how to implement them. So one of the obvious differences is that for the feature filtering method, you use different method um, compared to the one that you use for modeling. But for the wrapper, you choose the same model here, the same algorithm for selecting the feature and testing. So that's why they call it wrapper. You wrap around your environment using one algorithm. Okay. We also have this feature weighting. Feature weighting is just to give you the weight for individual feature to determine how they are relevant with respect to your data set. So we can put number here. For example, we have this column. Kan? So once we select all of them, basically they are all one. Or if we want to use only 3 of them, so we put 1010 lah. So we don't use this, we don't use this. Or we can put this one as 1.5, this is 1.2, and this is 0.1. So that means all the value here you multiply with this value to have a better adjustment on the differences of value. Okay, but all this thing, the weightage is can be nullified by using the normalization. Okay? Okay, let's take a look at this example here. Okay, in this example, we have this Wisconsin breast cancer. So what we will do, we will use this algorithm to classify them. So we have 32 features, 32 column, and one of the feature is the ID number, not relevant. Another one is the cancer diagnosis. So this is your label. And the other 30 are numeric value laboratory measurement. So notice that for all this value, we will have different range. So we can use normalization method, for example, min-max or the z-square to normalize them. Okay, so we have around 569 example of cancer. So we read our data from this data set. String as factor is false. That means string of character will be treated as string. Okay, so we have 32 variable, 569 object. Okay, and these are all the value that we have. And then, okay, we want to remove this because they are not relevant. So we say we update our data, but we remove the column number 1. So now we only have 32 variable, not 31 variable. Okay. Okay, now we can also look at the table for the diagnosis. So we have benign and malignant, this number. Okay, if you look at here, our label is supposed to be this one, but this is character. So we want to change this one to label. Okay, so we can use this one. We say, okay, we check what are the value for the diagnosis. They are in string of character. So we want to change this one to a factor, and this is the label that we have. This is label. This is the label that we have. Okay, so this is just converting your diagnosis to be benign and malignant. So now we have this as your label. So no longer B, but benign. Okay. Okay, now we look at the proportion of data that we have. We can use this proportion.table, and then we look at the percentage here. So how many percentage belong to benign and how many percentage belong to malignant. Okay, and then we also have the remaining 30 features of all numerical value. So if you look at this one, this is the radius, area mean. So look at the mean here and max. They have different range of value, right? So some are big, some too small. So that's why we need to normalize them. Okay. So for this one, we are looking at the function. This one we normalize. We define a function that will receive x, and it will normalize that value. Okay, for example, this one we normalize 1, 2, 3, 4, 5. The range will be like this. So we just pass the value here in the normalized function. So how do we apply this function normalization to the dataset? Okay, so we will apply the method normalize here for the column number 2 up to 31. Column number 1 refer to the label, so we don't have to normalize them. So column number 2 up to 31, we normalize them, and then we save as data frame. We put in another variable here. So if you look at the range of value here for the area mean, we have 0 and 1 here. Okay. Okay, now we divide them into training and testing. So we take the normalized value here, and then we say 1 up to 469 row will go to the training, and the remaining will go to testing. Okay. Okay, now we have those two. Okay, we also need to extract the label for the training. So we go from row number 1 up to 469, and we only take the first column. Similar to this, we take the remaining column, but the remaining rows, then we only take the first column here. So these two will capture the label. Okay. So next, we will install the package class here. So KNN. So we call the KNN. We provide them the training dataset, the test dataset, and the class, the label, and the K that we have. Okay. So how actually we call them? So basically, we are giving the training, and then the testing dataset, and also this is the label of the training dataset. And this is k equal to 21, means 21 label. Okay, so we call this KNN. So the model that the result that we get is here. This is the result that we get. Let me This is the result that we get. Okay, so how do we look at the result? Okay, so no, not result. This is the model. This is the model. So we use the model here to do the prediction. Not really. This is the result that we have using k equal to 21. The next slide just show you that we can have two predictions here using k equal to 21 and k equal to 10. So we have two predictions here. So we want to look at what are the accuracy for these two. So we say, so this is just to plot the confusion matrix. So the first one is using the prediction of the first model, and the second one is use the prediction of the second model. Okay, and we look at this one. So this is true positive, true negative. The error is 2 out of 100. Okay, for this one, the error is 4 out of 100. Okay, so we can say that k equal to 21 give you better accuracy. So the moral of this example is that we need to try K21, K22, K15, K10, and so on. So this is another issue that we are having at the moment. What is the value, the best value of K? Who can, because different data set will give you different behavior and different result. So that's why for new data set, you need to run few value of k, and then based on that, you can decide what is the best k that you can use, and you keep that k for once you want to deploy your model. Okay. Any question? Any question? Okay, so both these will have the step by step. So I will share the data in the ITEL. So I will let you do the practical, and of course there'll be our assignment coming in. So based on the ITEL here, let me